definitely trying, and it is, I hope that I am sending data to the right YouTube link, because I know David Englehart will smack me if I am not going to the right location. All right, so Q&A Friday. It is time. Whoa, what the heck is that? So Q&A Friday, and Tom Dimitrovich here. I was just on the phone with my friend Donnie Cook, and we had a great discussion, but that's why I'm late. Okay, so questions and answers. I make sure I got a green. I had a good question. I had a couple good questions coming up. So first off, we had a question on receptacle height. Hey, David, there you are, brother. Thank goodness that we got the right link this time. Okay, so receptacle height. I have a question which I'm trying to get I'm a little discombobulated because, again, I wasn't ready. So let me go to studio, and I'm going to take a look at some of the questions. Before I get started on that, remember, on Tuesday of next week, every Tuesday, I'm going live next Tuesday. Good morning, Ryan Jackson. So Tuesday of next week, I'm doing an IAEI News Live. So hashtag, I'm getting better at this, not pound sign, it's hashtag, which technically is the pound sign, IAEI News Live. If you search for that, you'll find the sessions. But I go live on Tuesday at noon. And this Tuesday, I'm going to have Tim McClintock, and we're going to be talking about resources for water damage equipment, water damage solutions, things to think about during these times of flooding and whatnot. So receptacle height is the point that we're going to catch this time. And the question was, I'm looking for it. The question was, is there a minimum height to install a receptacle on a wall? Now, I can read that a couple ways. I can read it the way it's written. Is there a minimum height? And I can read it, is there a maximum height? The only place, now, when you're saying on a wall, I don't know if they're talking about countertop space, or if they're talking about general wall space. If you're talking general wall space, you're in 210.52 dwelling unit receptacle outlets. And in the parent text of 210.52, it says, this section provides requirements for 125 volt, 15 and 20 amp receptacle outlets. The receptacles required by this section shall be in addition to any receptacle that is as follows. And if you look at item 4 on that list, it says located more than 5.5 feet above the floor. So what I would say is the receptacle outlet requirements in 210.52, that height is going to be 5.5 feet. So I can put it 2 feet off the floor. I can put it 3 feet off the floor. There is no minimum. I can put it in the floor. I wanted to, right? I can put it on the wall, anywhere in the wall. Now, when you get into the floor outlets, there is floor receptacles. Receptacle outlets in or on floors shall not be counted as part of the required number of receptacle outlets unless located within 18 inches of the wall. So if I could be in the floor, but I got to be within 18 inches of the wall to be permitted to be counted as part of the number of receptacle outlets. So I would say there's no minimum. A maximum is 5.5 feet. As in 210.52, or hopefully that helps you. I just gotta make sure that I'm live right now. Just letting my wife know, because I'm not sure if she has usually she calls me twice if there's an emergency. So anyway. All right, so 21052.4 would be, I think, the right answer. What I would direct you from a height perspective of a receptacle on the wall. Now, if you're talking about wall space, or I'm sorry, counter space, like countertop and work surfaces, there are other requirements, and those are in, again, 210.52. But I would point you to 210.52 Charlie C for countertops and work surfaces, because there are limitations on where you can place your receptacle outlets with regard when serving a countertop or peninsulas and all that good stuff. So be mindful of that in the list. All right. Okay. So, let's take a look. The other question I got on selective coordination. So this came in on my work email. I've got like 6 different email addresses. I don't know about you guys. I've got one for my YouTube channel. I've just got too many. So let's just do a quick search in here. And it was a selective coordination. And let me find, it was about the definition. There it is. All right. Okay, Tom. It says, we are well into the differentiation between coordination and selective coordination. And he says on coordination, he has parens time. And when he says selective coordination, he says all times, all currents. However, in our electrical industry, things are not clear. Many published items that are on the internet wander around and even circle back to saying that selective coordination can mean 0.01 seconds or even 0.1 seconds if that is what the engineer of record wants to define it as. Life would sure be easier if the NEC would just say it clearly in black and white, but it doesn't. And they put the definition, which is coordination selective, right out of the National Electrical Code. And it says, I am discussing this with an engineer now who is creating his emergency and life safety circuits with multiple panel boards levels and 70 amp breakers feeding 60 amp circuit breakers. This is exhausting. Mark. Okay, Mark. I feel your pain. I really do. So let's do this. I haven't opened it yet, but I'm going to open up. I do have a slide deck that talks about selective coordination, and it's probably, I'm just going to grab one here, so bear with me. Okay, so let's read the definition of coordination. If you go to Article 100, for this, I have a hard time with this because for me, it seems so simple, and I don't understand. Sometimes I don't understand why people don't understand it. I had a professor one time, Dr. Hasnadar. Dr. Hasnadar, and I think I understand his comment. One day, he was my digital professor, and we were going over microprocessors and laying out motherboards and stuff like that. And I was very good at it. At least I thought I was very good at it. I mean, I really got into it. But there was a discussion that he had, and he was presenting something on the board. And he looked over at me and he goes, Mr. Domitrovich, he says, you look confused. And I said, Dr. Hasnadar, I am. I don't understand I don't understand this, whatever it was he was showing. And he tried to help me understand. And then, and I wasn't alone. Nobody in the class understood. And then he looked at me and goes, Mr. Domitrovich, He goes, I don't understand what you don't understand. And I said, we both have a problem. And I feel the same frustration that probably he felt with me in regard to selective coordination, because to me, it is very easy. I mean, I've been doing it for a very long time, even before my days at Eton, because I used to do selective coordination studies and I used to help teach it with Frank Angelini. Frank Angelini, one of my mentors, great mentor. If you're out there watching, Frank, I miss you, brother. He taught me a lot about selective coordination, and when I worked with Gilbert Commonwealth, which is now Parsons Power. So I am going to try, let's take a look at the definition first. And I think this is the 2017 version. So, man, I know I have a newer version of this selective coordination. Whoops. Don't hit Control R on your computer. So I'm going to do selective coordination. I'm just going to search for my PowerPoint again. Forgive me. I was not ready for this call because I was on another call. Eden Safety Awareness, ASHI, taking care of ASHI, selective coordination 2021. That was the one I think I had open. Yeah. All right. Well, I'm going to put this up. And then I will read the, I'm going to read the PowerPoint. This is the definition. This says, yeah, because the 2020 code, I'll tell you what I'm going to read the 2020 code. This is the 2017 language. I'll read the 2020 language for you. All right, coordination, localization of an overcurrent condition to restrict outages to the circuit or equipment affected. Stop right there. Localization of an overcurrent condition. What is an overcurrent? Let's read the definition of what an overcurrent is. What is an overcurrent? Overcurrent is any current in excess of the rated current of equipment or the ampacity of a conductor. So, and it says it may result from overload, short circuit, or ground fault. So localization of an overcurrent condition to restrict outages to the circuit or equipment affected. Now, regardless of anything else, before the TCC curves, before we get into any of the technical details, what do we know by that very first portion of the very first sentence? Actually, it's like one big sentence. And that's got to be the longest sentence. It's got to be more than one sentence. So, man, it looks like it is one big sentence. Okay, so up to the very first comma, what does that tell me? That tells me if I have a fault, I want to localize the overcurrent condition and restrict my outage to the circuit or the equipment. So if I have a motor that has a short circuit into it, whatever is directly feeding that motor, I want that motor to be taken out, nothing else. So that is the concept. And whatever it is I need to do to understand the performance of my overcurrent protective devices, then I need to do it. So that is the basic fundamental principle we cannot lose sight of. Regardless of anything else that we do, ask yourself that question. For an overcurrent condition, which could be a short circuit, a ground fault, or an overload, I want to localize the problem. I don't want to have a widespread outage outside of just taking out the equipment that is affected. Now, where I think the confusion resides is when we start talking about curves like this. Let me move that out of the way and move this over here. So I am going to just make this bigger. Okay, so these curves here's why I use this example. I'll tell you exactly why I use this example. I had a very good electrical engineer, very, very smart individual, sent me this curve, which is a BAB. This is our BAB breaker. This red one, that red circuit breaker is a BAB 20 amp breaker. And the 150 amp breaker is an F150, not the truck, the breaker. So it's an F frame 150 amp breaker, which is upstream of the BAB 20. And they sent this image, this TCC curve, and they said, wow, look at the great selective coordination of these two breakers. Because look, I mean, you got separation all the ways down to 0.01 seconds. And I said, what's the fault current? 4-word sentence. When I emailed it, I responded back and said, what's the fault current? And that individual called me. And it was a she. And she said, what do you mean, what's the fault current? In an argumentative fashion. And I said, well, I can't answer the question of selective coordination without knowing the fault current. So think about the definition we just read. And this is this. So what she said was, in a frustrated manner, she says 10,000 amps. And I went, oh, okay. 10,000 amps, then they don't selectively coordinate. And she said, what are you talking about? And I said, take a look at the definition of selective coordination. It is the localization of an overcurrent condition to restrict outages to the circuit or equipment affected. I said, what's going to happen when these two breakers see 10,000 amps flowing through both of them? And there was a pause on the phone, and she said, they're both going to open. And I said, is that a selectively coordinated system? And she was like, oh my gosh, you're right. And then it was like a light bulb went off, and she was like, I get it. And so I'm going to take you to a different conversation now. So then I take these same two breakers, because it was a revelation for me that somebody would forget about that fact, especially a person who I had a lot of respect for with regard to technical knowledge and engineering. But that individual did not do selective coordination studies for a living, right? That person was just not in that world all the time. And for this, and you know, her comment caught me aback and brought a realization that, wow, this is not something that everybody really understands, because the curves seem to imply great selectivity for all currents, but that's not the case, because we know. Now, I'm going to fast forward this to a different conversation. So I was having a conversation with another really, really good engineer that I have a lot of respect for, technical wise. And I made the statement, I said, wow, you know, this individual who we both knew at the time, I said, I was surprised, and I explained just what I'm explaining to everybody, all of you. And that person, I threw these curves up on, and I drew them on the whiteboard. And they said, well, those selectively coordinate. And I went, well, not for 10,000 amps of fault current or 5,000 amps of fault current. And they went, I have separation of curves all the way down to 0.01 seconds. Those selectively coordinate. And I'm like, no, they don't. Because I don't know the fault current. If the fault current is 10,000 amps, I can tell you they don't, because of the definition and because I know what the goals are. To isolate the fault current, that 20 amp breaker should be the only one that opens on those fault currents. Now, we can have an argument and a debate on whether or not it should be the three-phase bolted fault current value, but regardless of that argument, That argument is not, if I look at the National Electrical Code, that argument's a moot point because it's very clear that I have to make sure that these work all the way up to the three-phase bolted fault current value. So, but even if I say, well, talk about ground fault current, I still have the same issue. What is my fault current? What current are you going to selectively coordinate these two, or coordinate these two if it's less than the three-phase bolted fault current value? So, and that individual disagreed with me again, and they said, no, that downstream breaker will open and the upstream breaker will remain closed even for 10,000 amps. And so how do you handle that one? I mean, how do you argue with somebody that is not the case? You have to run a test, right? And I thought, well, I can't run a test right now because, I mean, I got to get lab time, and then I have to justify the money it's going to take to prove something I already know. And then I dawned on me, we already did the testing. In fact, most manufacturers have done the testing already. So if you go to Eaton Selective Coordination, clicking on the wrong click. So I go to Eaton Selective Coordination, and there's a tool out there, which is good, but that's not what I want. Let's take a look at this application paper. Look what this says: Selective Coordination Application Tables. Selective Coordination Tables. So I am going to find the page. Here we go. I said I had a BAB, so here's my BAB. I'm looking for the right breaker pair. All of these are power defense. What it is, this is a thermal mag breaker. So that FD 150 is this PDG2, which is the F frame. See the F right there, and a G frame. 150. So there's my 150 amp frame breaker. There's my 20 amp BAB circuit breaker. And how you use these tables. These tables, tested pairs, they tell you when what's over here on the left-hand side is your downstream circuit breaker, and what's across the top is your upstream circuit breaker. So in our case, the downstream is this 20 amp BAB breaker, and the upstream is this F150, the circuit breaker, not the truck. I'm going to zoom in for you, and here's my 20 amp, and there's my F150, 1,500 amps. So I know if I had anything greater than 1,500 amps, both of these devices are going to open, right? And what does the definition say? The definition says localization of an overcurrent condition to restrict outages to the circuit or equipment affected. I can stop right there. If I know my fault current is 10,000 amps, or if I know my fault current is 5,000 amps, if it is 2,000 amps, I know based upon those tables that anything greater than 1,500 amps, both of those are going to open. Does the system have to be fully rated in lieu of series rated? Yes, David, they have to be fully rated. Now, let me just say this. If my fault current, so for this pair is 1,500 amps. If my fault current is less than 1,500 amps, would I be buying a series rated system? No, because everything is rated to interrupted. If you are looking at and buying a series rated system, it's because your bolted fault current values are high enough to exceed the interrupting ratings of that downstream breaker. And if they're high enough to exceed the interrupting rating of the downstream breaker, then the upstream breaker is going to open to help protect the downstream breaker at those values. So now, can I selectively coordinate? Can I buy a series rated system and still selectively coordinate? Well, sure, if your fault currents are low enough, but you don't need to series rate it, because if they're low enough, then you will interrupt them. But if they're high enough that you need to series rate, that means both of those devices are going to open to clear the fault together. And that is counterproductive to the very first portion of that sentence, because you will not be localizing the overcurrent condition to restrict the outages just to the circuit or equipment affected. Because remember, what I'm not showing here, let me put it in there. Let me show you. Let's do this. I'm going to take this. Okay, so this is my circuit that I'm talking about, and what I'm not showing you that I probably should, let me ungroup things, is that I have more than just those two breakers downstream. All right. So I could have multiple 20 amp circuits. I could have two 15 amp and one 20 amp. If I take that breaker out, I lose all three of those, not just that one. So I was only showing one breaker, but in reality, we know that panel board's going to have more than one breaker. So the issue I have, and what this individual is saying, that things aren't clear. I mean, if I just go back to his email, it says things are clear, that the definition needs to change. And I'm not sure how I would change the definition to be any clearer. Now, we all know that when we don't agree with something, then we will try to find, it's the same argument that we have with GFCIs. We have a GFCI requirement for crawl spaces, and someone does not want to put a GFCI in that crawl space. So all of a sudden, we don't know what a crawl space is, right? Whatever the room is, the inspector says that's a crawl space, and the contractor says that's not a crawl space, and they go back and forth. And then whoever, then they'll say, well, we need clarity in the code for a crawl space. No, well, no. You just needed to provide GFCI protection. All of a sudden, we don't know what a bathroom is. We don't know what a kitchen is. We don't know what a laundry is. I mean, we had that debate on panel 2. We saw public inputs. We put GFCI requirements and AFCI requirements in laundry circuits, and all of a sudden, nobody knew what a laundry was. And they said, well, what about this? What about, they gave you all these scenarios. Why is that? Because somebody's just trying to say, look, I don't want to have to do that. So that's what typically happens with selective coordination. They don't, because it's not easy. Because I just don't pick two breakers based upon, I call it Picasso. If you're just looking at two trip curves, looking for space, in my opinion, you're like an artist. It's pretty pictures. You're not doing any analysis other than looking for space in between two curves. And you may say, well, it's difficult to get space in between two curves. So I have to go through a bunch of different breakers and keep plotting them to see how do I get clear space on over the length of that curve. Well, yeah, but that's not a technical evaluation. All you're doing is training somebody to plot a curve and look for space. And now, if you told them you have to do an evaluation of these two breakers based upon some level of fault current, even if you said, I'm not going to do the three-phase bolted fault current, okay, that's fine. You can pick something less. What is it? And what's your justification? So when I used to do studies, and I did studies like for, I did some studies for nuclear, and nuclear did not settle for anything other than selective coordination. But some industrials, what I would do as a design engineer, if for example, I took this project here and I said my fault current, my fault current is, I'm going to draw a line. I'm going to do an insert, and I'm going to go to shape, and I'm going to go to line, and I'm going to say my fault current is, so these are time one. So that's 10,000, 20,000. I'm going to say it's, that's 1,000. No, that's 10,000. So this is the BAB 20. So that's 1,000. I don't know. Let's say my fault current is, I don't know. Let's say my fault current is right here. I'm just going to draw a line, whatever. The value of it is is not important right now. So let's say my fault current is well into the instantaneous region of that F150. And I would go to the customer and I would say, okay, look, you don't selectively coordinate to the bolted fault current value. I would also plot a lower value and say this is the, I don't know, the arcing ground fault current. I would say, okay, you don't selectively coordinate to the three-phase bolted fault current value, but the most common fault in a power distribution system is the arcing ground fault. So I plotted that value and you coordinate to that value. And I would tell the customer, if you wanted to selectively coordinate so that you know you will never have the possibility of a cascading event, then I'd say you have to make a change. What's the possibilities? What would you do? I could add a transformer in to lower the fault current. I could increase the size of that 150 amp breaker to a larger breaker and move the instantaneous to the right. I would give the customer the options. I don't make the decision for the customer. I'm basically doing a study. If the customer said, I want a selectively coordinated system and I want you to design it that way, then I would pick different devices. I might put in a transformer in my design. So regardless of that, I would have to make adjustments because I know that for a given fault current value, if it is the three-phase bolted fault current value, they're both going to open. I can't ignore that. Now, I think, and to his point, to Mark's emails point, he said about 0.1 versus 0.01. So why do we use the terms 0.01 seconds? 0.01 seconds is the bottom of this TCC curve. Why is it 0.01 seconds? Why does the TCC curve cut off at 0.01 seconds? SKM and EDSA and Easy Power all default to 0.01 seconds. I could plot it lower than 0.01 seconds if I wanted to. In fact, the TCC curve. So if I go to eaton.com/TCC and you just wait a little bit. Oh, Eaton TCC curves. I thought it was /TCC. All right, here we go. So I'm gonna go to a molded case circuit breaker. I don't know. I'm gonna try the FD breaker. I'm gonna go to Series C. I'm just gonna pick a breaker. Something tells me that here we go. All right, look at this. Here we go. Here is a this is that FD breaker, but this is a 50 amp, and the curve for 150 is going to be in here as well. But let's take a look. All right, here is time. There's 1 second. There's 0.1 seconds. There's 0.01 seconds. And look, I plot it always down to 0.001 seconds. So for that that's a 50 amp breaker. There's my 0.01 seconds. If I plotted a 50 amp circuit breaker, it would cross over and basically get cut off at the bottom of a time current characteristic curve if it was cut off at 0.01 seconds, which is right here. Look, that says 0.01 seconds. That is where it would cut off. You would see the curve the instantaneous cut off right there, and it wouldn't show you anything past that. But in reality, there is data that could be shown on a selectively coordinated system on the TCC curves if it's put into SKM and you increase the margins within what's plotted on a TCC curve. But rarely do we do that. We don't do that. Whenever we get to these fault currents that are high enough, we rely on these tables now. That is what we do. We pick these tables. These tables will tell you what will happen to those two breakers beyond a certain current value. I can tell you they'll both open or they won't. When does a system have to be selectively coordinated other than for emergency systems? Healthcare. I knew, David, you were going to go there. Healthcare does not selectively coordinate. So let's take a look on what does. So I believe in this, I have the, I think I have the sections in the code that require selective coordination. I think I have it in here. 700 does 701, Article 701, 708, right? So 701 are what? Your legally required standby systems. 708 is your critical operation power system. Okay, 690. So here we go. 620. 620 requires it. 620.62. Now this is probably based on the 17 code. Oh yeah, you know what? Let's go to the index. Good point. Let's go to the, I never thought, see that, David? I never really used the index at all. So let's take a look. He's going to use the index. I mean, David wants to cheat. David wants to cheat. That's okay. We're going to go back and find the easy way. Selective coordination. And what he's saying is on the back of the code book, go to your index and look up selective coordination. Make sure, there it is. No, boy, no, it doesn't, David. Selective coordination, it tells you to see, oh, coordination. You got to go coordination selective. Oh, Mohammed, you missed it all, buddy. Man, coordination. I got to look up coordination. I got to go to the C's. All right, coordination, COO. There it is. Look at you, David. All right, so coordination. Coordination, electrical systems, coordination selective. Coordination. Legally required, 701.32. Information technology, 645.27. Healthcare, 517.31G is not selective coordination. Selective is 620.62. There's your 620.62. 645, there's your 645.27. 695, so 645 is modular data centers. 695, 695.3C3, 695.3, C, whoop, 3, there it is. That's for 5 fire pumps. 700.10B, 700.10B. 700.32. All right, so this went from 700.28 to 700.32, and then 701.32. This is no longer 27, so 701.32. And it's also in 708, so the index should be 708.54. There it is, 708.54. And we already covered 645.27, and we already covered 701. So those are the locations where it's required. Now, what does healthcare do? Healthcare is 0.1 seconds. Healthcare did not pick a lower value of fault current at all. Yeah, this is it, Mohammed. I'm talking selective coordination, buddy. Yep. So healthcare, what healthcare does for 0.1 seconds, you don't need to hire an electrical engineer for coordination. If you're going to do 0.1 seconds, you don't have to calculate fault currents. You don't have to evaluate your overcurrent protected devices to any fault current value. What you do for 0.1 seconds, and I might have some slides in here that cover 0.1 seconds. 0.1 seconds makes your life easy. So here we go. There's 0.1 seconds. So let's talk about what it does. 0.1 seconds. So if I have these two breakers. I have an upstream breaker and a downstream breaker. My available fault current is 20,000 amps. I know I am well into the instantaneous region. I know for a fact they will both open on that bolted fault current value, or if that's the ground fault current value, I don't care. If it's the arcing fault current value, I don't care. I know for 20,000 amps, they're both going to open. So what 0.1 seconds does is it looks for separation of their time current characteristic curves. Now, I know that I have separation above 0.1 seconds, but below 0.1 seconds, I have this heel down here. But what we do in a healthcare environment, we cover up the anything below 0.1 seconds. You don't want to see it. In fact, my little ruler here is not good. I got to get rid of it all. So I cover everything below 0.1 seconds, and I make sure I have separation of curves above 0.1 seconds. But then, as engineers, we know for 20,000 amps, even if I hide everything below 0.1 seconds, I know for a fact those will still open. And what do? We just ignore that fault current because it says without regard to fault current magnitude. So I don't have to compare the performance of overcurrent protective devices with regard. I don't have to. I can elect to. I can always go above and beyond bare minimum requirements of the National Electrical Code, but I don't have to. I can ignore the fault current. I can hide everything below 0.1 seconds and look for separation of curves above 0.1 seconds. I may know for a fact that if a ground fault current or a bolted fault current occurs and they both see it, that they will both open. I can know that for a fact, but I'm not required by code to address it. I just need to make sure that I coordinate in the overload region of those two trip curves. Now, could I have a fault current that is lower than that instantaneous pickup and these actually selectively coordinate? Yes, I could. Likelihood of that is very low, but I could. And I could do the same thing with fuses. I can put those fuses, I could put a 600 amp fuse upstream of a 500 amp fuse. I would guarantee they're both going to open, but I would meet the requirements of 240 of selective of coordination for Article 517. So that basically, and I think the whole introduction of 0.1 seconds really confused a lot of individuals. And I think that there are a lot of people that will look at these curves right here. They'll look at these curves right here and they will say, gosh, they are beautiful. They selectively coordinate. Look at the separation of curves all the ways down to 0.1 seconds. And they stop right there. And they are technically incorrect because I need to evaluate both of those overcurrent devices with regard to current. And in the case of selective coordination, it's the maximum three-phase bolted fault current. In the case of coordination, I don't need to evaluate it. So they coordinate. Yeah, though they coordinate. They look great for a coordination perspective, but they do not. I haven't done any evaluation. If I just looked at these curves and said they coordinate down to 0.01 seconds, I haven't done any evaluation of fault current. All I know is I have separation of curves down to 0.1 seconds. And that value on this curve right before that leading edge of this blue curve, which is the overload region of that circuit, then I know that the downstream device will open and not the upstream device. Hey there, Robert from Omaha. Greetings and salutations. All right, so that and that question, I mean, I get that question, in my opinion, way too often. I don't know why. I think it's very clear. And with all the data that we have today, especially in the selective coordination tables, I can tell you an F-150 upstream of a BAB20 or a BAB30, you put 2,000 amps through both of those devices, they're both going to open. If that's your goal, if you don't care about that, then don't worry about it. If you're required to worry about it per the National Electrical Code, then you've got to address it. If you want reliability, if you have an outage, if you want to maintain a reliable power distribution system for other reasons other than the National Electrical Code or safety, it could be money for you, then you need to consider that and do that evaluation. I know too many engineers who do not do that evaluation, who do not compare overcurrent devices with any fault current. They hide everything below 0.1 seconds, don't calculate fault current, look for separation of curves, and they think, I'm good to go. You are, if that's your goal. If you don't want a cascading event because of any type of fault current value, whether it be ground fault, arcing fault, whatever, then you have another issue. All right, so I don't know how else to explain it. And I've explained it that way before. In fact, to this individual, I've explained it. To the person who asked me that question, I've explained that. But for some reason, it's still unclear, and I don't know how to clear it up. I just don't know how to clear it up. All right, I'm gonna see if there's any. Okay, I do have. I thought I had. Still got 10 minutes, so let's take a look at my LinkedIn. I'm gonna see if I have any other questions. My Q&A. Whoop. Q&A. Nope, that's not there. Q&A Friday. I'm just going to double see. On some of these, I wrote down questions, and we answered most of these. Will that PowerPoint be available for us journeyman schmucks looking to better master electric, but still a schmuck? Up to no bod high. Yeah, you know what? Yeah, I can get that to you. I would say go out to my website and subscribe. If you go to thomasdimitrovich.com, go to thomasdimitrovich.com, and you'll see the Buck 41 Club out there. You can go to resources, and you can register. So it's free. Just give me your information. And then I have a members only area where I will put my slide deck up there on selective coordination. And it's a Q&A, so it's got a question and answer type of deal. So I can do that. Just register for that. And then you'll be able to send me an email too and ask me for it. But I'll put it up there on the members only area, which is, again, free. I'm not charging anything for that. I just want to make sure I keep everybody in the family and everybody knows whenever I make changes, or if there's a correction, I can get a correction to everybody, all that good stuff. All right, so let's take let me go back to my bada bing, bada boom. All right, current limiting fuses. We answered that one in the last call. How does a current limiting fuse constructed? We talked about that. Covering a 240 volt class A GFCI protection. I haven't seen any issues, but manufacturers are recommending them not to be used. Quite a conflict on AC units. Thanks, bro. William, 3 days ago. Well, that was 3 days ago last week. There's no requirements in AC to put a label on a disconnect. All right. Well, let me answer this one first. It says selective coordination with tested pairs. Selective coordination with tested pairs in fuse applications. One issue with this is that many disconnects accept different fuse manufacturers. There's no requirement in the NEC to put a label on a disconnect using this method to inform a future service person to replace only with a certain manufacturer's fuse. And this has come up before. In fact, I think there was a public input for the 2023 cycle. I'm going to go quickly take a look at and see if they made any changes. But there was a view public comments. I'm going to look at the first draft report. Everybody has access to the first draft report. You can go up and take a look at the first draft report on NFPA's website for the 2023 code cycle. But I know this came up once before. So I'm going to look at 700.2032. 700.32. I'm going to see if they made any changes. All right, modifications. They added replacements. Where emergency system OCPDs are replaced, they shall be evaluated to ensure selective coordination is maintained with all supply side and load side overcurrent protective devices. Modifications. Where modifications, additions, or deletions to the emergency system occur, selective coordination of the emergency systems overcurrent devices with all supply side and load side OCPDs shall be reevaluated. So to this gentleman's point, there's no requirement. Now, be mindful. Yes, fuses can be replaced by different manufacturers. I could even put a different catalog number fused from the same manufacturer into that slot, which would be ungood. Could be ungood. With regard to circuit breakers, I could, I've seen many cases where I don't have my set points, right? I do a study and then nobody implements the set points in the field. And then when you get a cascading outage and they say, I paid for a selective coordination study and it still didn't work, and it's because you didn't program the set points. I can change a circuit breaker, and remember, I can put there's a few nice things about fuses, and there's a few bad things about fuses, and there's a few nice things about breakers, and a few bad things about breakers. But in any overcurrent protect device, I don't care what it is. If you replace an overcurrent device, if you change the settings, whatever it is, or you first install, breakers have settings. Fuses, you've got to match with the manufacturer. There's no marking requirement. And I thought there were marking requirements there were 6 public inputs. Let's take a look. Oh, yes, look. Michael Dempsey from Trinity Code Inspections put a public input in that said, equipment enclosures for selectively coordinated overcurrent devices shall be legibly marked in the field to indicate the overcurrent devices are selectively coordinated. The marking shall meet the requirements of 110.21b and shall be readily visible and state the following. Caution, overcurrent devices in this enclosure are selectively coordinated. Equivalent replacements and trip settings are required. I like that. And it was resolved, and the panel statement was the information referenced by the submitter is already available and required. 700.32 mandates that the, quote, selection shall be documented and made available to those authorized to design, install, inspect, maintain, and operate the system. So it is already required to be available. It's just not required to be marked on the equipment. So JW, great question. And I would say, just to this point, whether it be set points on a breaker or the actual fuse catalog number, those are all critical and they should be documented in the selective coordination study. All right, so let's look at this one. William Snyder. Okay, so AC units. Here's what's going on with HVAC stuff. What we've learned is that there are no UL requirements that test for and limit the amount of current that can be placed over the equipment grounding conductor for these units. Now, you could say, Tom, Article 250 in the National Electrical Code prohibits current on the equipment grounding conductor because of, what do they call that? Objectionable current. These words don't want to come to my head. So you could say, look, Tom, the code already says you're not allowed to have objectionable currents on the equipment grounding conductor, but I'm telling you, some manufacturers of HVAC equipment use the equipment grounding conductor. We've measured it. I have a video on my phone that shows, I'm just gonna try to find it here real quick. Albums, I think I can go to videos, right? There is videos. And we were in a location where we were doing a bunch of testing in this regard. And here it is. Look at this. 10. This is on an HVAC unit. 10.38, 10.4 milliamps flowing on the equipment grounding conductor. Now, what this is, you got to remember how the meter works. I've got over 10 milliamps flowing on this equipment grounding conductor. And it's looking at multiple frequencies, right? 60 hertz and up. And the question that the standard guys are trying to address is, will the higher frequencies kill you? Now, Dalziel did study up to 10 megahertz or whatever to 10 kilohertz. I can't remember the number, whatever that number is. Dalziel did a study across a spectrum. And I'll tell you that this one and others violate that. Some of these are 60 hertz currents. They're putting, because we're not requiring the two hots, they're putting two hots and some loads, they're shunting current to the equipment grounding conductor because there's no neutral, right? Required to be pulled to those locations. So what we're experiencing right now is some units have currents going over the equipment grounding conductor that can cause a GFCI to trip. Not all. That's the other thing to be aware of, not all. And there's some units that are not the high efficiency units that are using that equipment grounding conductor and not compatible with a GFCI. And what do? I mean, is the next question is that a safety issue? I mean, we already have a body count, right? And there's another, I went out to the CPSC database, and you can find people who work on electrical equipment, who work on HVAC units that have died working on electrical on those units. So, I mean, they're outside, they're in the dirt, and yeah, their tool has to be plugged into a GFCI, but that piece of equipment, whether it be 240 volts or whatever it is, 120 volt circuit, whatever it is that they're working on, it's not GFCI protected. And if there's a problem, a wiring problem, if you lose that bond and now that case is energized and current's going to flow as soon as you touch it, and we've already seen death associated with that. So we don't recommend, I would never say, look, don't put GFCI on there. I mean, Panel 2 just approved a tentative interim amendment for some AC units, not all. And I'm not sure, I think it's gone through and it's probably out there on the website. But are there some units that cause earth leakage and use that? Then, David, no, I'm not going to have a modernization week today. Yesterday's was the last one. We had a conflict with today. So, and I think it's related to bourbon. I'm not sure. But in any case, no, it's not. We're not going to have a 5 o'clocker today. And it is 1 o'clock. So no 5 o'clocker today. You got your evening free. But I do have one more that we have to schedule for industrial control panels. So in any case, my comment with regard to the HVAC equipment is stay tuned, because in my opinion, we're going to see more dialogue around those units. And in my opinion, the standards have to change for those units in some cases. And the TIA is going to give you a stay of execution in that regard. But be mindful of the protection. And I would let people know about it. I would let the homeowners know about it. I would let whomever it is know that we do have recorded deaths on these units, unfortunately. And we know that there is an intentional use of that equipment grounding conductor. And the verdict's out on I can tell you it's a safety hazard, and that's why we've given a delay, and hopefully it will be addressed. I'm not sure what the right solution is, but for some there is going to be an exception for some HVAC equipment. All right, so I don't know what else to say on that one with regard to AC units, but that's William or Bill Snyder. That's basically what I know there. And I'm knee deep in it, and I've measured it, I have witnessed it, and I have people who would say, "Hey, my HVAC unit is tripping," and I would say, and they're going to put it on a standard thermal mag breaker. Well, measure. You have the equipment. Measure what's in the equipment grounding conductor. Tell me if you feel comfortable with that. I don't. I wouldn't feel comfortable with it. You got a big metal object outside in the rain. Anyway, I'll get on my soapbox. Now, what I would suggest and some people, this is a debatable item, I would suggest putting ground fault protection of equipment on it. Put GFPE at 30 milliamps. You at least have something so that if there's a short out there, if there is if a ground fault current is flowing, you're going to probably be greater than 30 milliamps. The one that killed that child was definitely greater than 30 milliamps. So you can isolate a problem before somebody touches it if you provide some level of protection outside of the thermomagnetic circuit breaker. So GFPE is something, some level of additional protection. And we do something similar in marinas. Think about what we do at marinas. We have 100 milliamps going out to the dock. We have 30 milliamps for feeders on the dock, and we have 4 to 6 milliamps for when you're plugging things in at 15 to 20 amps. So the 30 milliamp ground fault protection of equipment can give you some level of protection. It would seem the standard needs to reject the difference in current in the AC units and stop using the EGC for control circuit transformers. You know what, David? You are right. And there should be limitations because some of these might be high frequency leakage currents. I don't have to shunt those leakage currents to the neutral or to the equipment grounding conductor. If I required a neutral, I can use that neutral to bleed off of any of those currents that I need. Say it's an adjustable frequency drive or whatever. If I am going to put caps in to filter things inside my unit for whatever reason, I'd rather do that to the neutral than the equipment grounding conductor. But again, that takes a design change of the HVAC unit. It takes probably a change in the National Electrical Code, although I'd argue that if the instructions for the unit said pull a neutral, you'd be pulling a neutral, right? I mean, look at what we did with dryers circuits and whatnot. Look at what we did with the light switch, where they were using the equipment grounding conductor to power electronics inside of these occupancy sensors. They're prohibited now from being used. The code says you can't do that. And I don't know why we create a double standard for an HVAC unit. I mean, think about it. We have a light switch that the National Electrical Code and the entire industry, they're ready to rip their shirts and say, you're using the equipment grounding conductor to power these electronics on that light switch, that occupancy sensor. That's a violation of objectionable currents. And the code changed in multiple locations to prohibit the use of those types of light switch or those occupancy sensors. Yet, HVAC, 60 amp circuit, we want to give forgiveness. We just say that's the way it is. Why? Because it's tripping a GFCI. And rightfully so. Why is it that we hold a double standard between the occupancy sensor and an HVAC unit, condensing unit that's installed outside that has already killed at least one child and others based upon CPSC data? Why the double standard? I don't think it should be there. I agree. It's probably going to take some of those manufacturers to make changes to their products. Don't disagree with that. My heart goes out to them. We're giving them some time. I just think it needs to happen. But that is a big metal enclosure sitting outside in the rain. I mean, I've touched them. I've walked by, leaned up against them. If there's a wiring problem, if I lose my equipment grounding conductor, I've got a unit that I can have current go through my body. I don't care what frequency it is. I don't want it going through my body. So in any case, that is what's playing out right now. And what's happening right now is standard. The standards sought to change, and the industry of those who make those units argued against changing the standard to limit and to correct the issue. So now you have an issue that doesn't seem to be on the track to get resolved. I believe it will get resolved one way or another. But I mean, and I've even suggested to NEMA and others that we should just create a list. There are high efficiency HVAC units available from very good manufacturers that do not trip a GFCI. There are split units that do not trip at GFCI. There's one or two manufacturers that I have seen, that I am personally aware of, that have issues that are causing this uproar. But there are manufacturers who have very good products that are completely compatible. So I said, let's make a list of those. And let's promote the purchase and sale of those products because of this compatibility. There's a reluctance to do that. But I think that would be an awesome list. But if at bare minimum, I would call the manufacturer that I deal with and ask them, which of your models work well in a GFCI? That's what I would do. And that's the one I would install. Just the way I roll. And I would put GFCI protection on it. So in any case, that's my story. That's how I'm sticking to it. It is 1:08. David, I will not see any of you at 5 o'clock today. I will see you at Tuesday at noon for the IAEI News live session. I'm going to have Tim McClintock with me, and we're going to have a great discussion around water damaged equipment and storms and all that jazz. So, and all of the resources, and he is right in the middle of all this stuff. And I might even see if I can get Brian Holland on there. He's out of Florida. All right. So everybody, thank you for tuning in. Thanks for what all of you do for electrical safety. And I'm looking forward to a nice 3-day weekend. I'm going to be working on hardy board on the outside of my house. So if anybody out there has experience with replacing hardy board in the middle of the sheeting, I've got some damaged boards that I have to replace. Hardy board is a cement-based siding, right? It's whatever. Yes, noon Eastern, Steve. Noon Eastern on Tuesday. But anybody out there who has really good experience on that, what I have is on the side of my house, I have a roof that comes down like this, and right where that point is, where the gutter is, I've got some water intrusion, so I'm going to have to replace those. So any advice, I'm taking it. Never done it before. All right, Nikolai Tesla, thank you for tuning in. Thanks, Steve, Felix, David, everybody out there. Have a great 3-day weekend. Enjoy yourself. Relax. Take care. Stay safe. And remember, please stay healthy. Until Tuesday, we will see you later. Take care. Thanks, Mohammed. Great job, buddy.